All right, for problem 1, we have the following information. We have the specific heat of ethanol, which is 0.588 calories per gram degree Celsius. We also have a density of 0.789 grams per milliliter. So we know that it's kind of weird because it's you're burning out ethanol and you're also warming it up. But the main concern is right here. As something's burning, whether it's ethanol or something else, it is warming 24 milliliters of it from 12 to 24. So we're going to set up our equation. Delta H is equal to mass times the specific heat change in temperature. So delta H equals mcat. Here, normally, if this was water, we could directly convert this 24 to 24 grams. In this case, the density is not 1 gram per milliliter, so we're going to have to convert it. So 24 milliliters, and I'm going to have a ratio here. I want to get grams, so I'm going to keep it the way it is, 0.789 grams per 1 milliliter. And when you multiply that across, you'll get the mass of my ethanol. So 24 times 0.789. And I get 18.936. I'm not going to worry about sig figs until the end. I know right here my answer can't be bigger than 3 sig figs. 1, 2, 3, 1, 2, 3. And then here it gives me 2. So I'm going to make sure my answer is now 2 sig figs. So that's how I usually do it. I kind of just calculate it as if, and then make sure my answer isn't bigger than any of my initial points. Specific heat is 0.588 calories per gram degree Celsius, and then it goes from 12 to 24, so final minus initial, and then that will be my equation. The grams cancel out, the Celsius cancel out, and you're left with calories. And when you do this calculation, 18,936 times 0.588, okay, and then times 12, I get 133.6124, etc. calories. So I start off with 2 sig figs. I'm just going to kind of round it off to here. So it'll be about 130 calories. So that will be what I have here. If you have it a little bit better or a little bit more accurate, 134, that's fine. I know in my answers yet, but 134. But if we're going to use 2 sig figs here, let me just make sure it is 24. Yep, it'll be 130 calories. All right, so that's that one. Number 2, we're going to burn octane. Octane is 8. So C8, and remember, for all hydrocarbons, it's 2N, 2N plus 2. So 8 times 2 plus 2 gives me 18. Now, first we want to find out what percent mass this is. So I'm going to try to find a place to squeeze everything in. Carbon has a mass of, let me see if I remember correctly, 12.01. Hydrogen has a mass of 1.01, and if we multiply each one correctly, so 8 times 12.01 plus 18.01, I get a molar mass of 114.09 grams per mole. I want to know the percent mass of carbon, so 8 times 12.01 is 96 divided by 114.09, and I get 84%, 84.2. The empirical formula is just this reduced. So I could divide both of them by 2, which will give me C4H9, and I can no longer reduce it. So that will be the empirical formula, C4H9, in the combustion equation. So remember, you have your fuel plus oxygen, and that will give us carbon dioxide and H2O. So this is a complete combustion. In real life, we're probably going to have incomplete combustion depending on what the fuel is. In octane, we're going to actually most likely get some incomplete combustion, but let's assume it is complete. So C8H18 is our fuel. With oxygen, it's going to produce these two. Let's balance the equation. We have 8 carbons here, so I'm going to put an 8 right here. Now it's balanced on both sides. I have 18 hydrogens here, so I have H2. So 18 divided by 2 gives me 9. So 9 times 2 is 18. So now I have 18 hydrogens on both sides, 8 carbons. Now we count oxygens here as 8 times 2, which gives me 16 plus 9, which will give me 25. So that means I need 25 on the left side, so you could kind of cheat. If it's O2, 25 divided by 2. If you don't like fractions, you could just multiply everything by 2, so it would be 2, 25, 16, and then 18. But this will be correct as well. The last part is if I had 2.91 grams of octane, how much moles or how many grams, it depends. Let's see, it's asking for moles. How many moles of CO2 and how many moles of H2O I have. So since this is based on molar quantities, we want to make sure we find how many moles of octane we have. So if we have 2.91 grams, we want to convert to moles. Here is my ratio or my molar mass. So I want moles on top. So that means the grams is on bottom. 114.09, and let's do that. So 2.91 times, or sorry, divided by 114.09 will give me 0.0255, and then it keeps going on. Now, like I said, let's just keep it in our calculator, and I'm going to multiply this with 8. So that means I'm going to get 0.204. Let me see how many sig figs we started off with. 3. So I'm going to keep it with 3. How many H2Os? So divide by 8 to keep my original number, and then multiply by 9, which is 0.23. Okay, so those are my two answers. Let me just check and make sure I did my math correctly. Oh, I didn't do these ones. So those are our answers right there. Just remember, so we got the moles of this one. The ratio of 1 mole is to 8. So whatever this is, I'm going to multiply by 8 to get this number. And then same thing, multiply this number by 9 to get this one. So that's how you do 1 and 2. For number 3, we have the following. So we have a candle that's being burned. We're going to burn 0.5 gram of it. Just remember, a candle's fuel is C25H52, and what's given is the molar mass, which is 3.5 times 10 to the 2. If you don't like that, that's 350 grams per mole. So remember, times 2, the decimal point moves over twice, 1, 2. And we want to find out how much oxygen, carbon dioxide, and water it's going to be produced. So just remember, this is a combustion. So C25H52, it's going to combust with oxygen. If this is a complete combustion, then we're going to produce only carbon dioxide and water. We want to balance the equation. So here we have 25 carbon, so I'm going to put 25 right here. So now I have it on both sides. I also have 52 hydrogens. So 52 divided by 2 will give me 26. So now I want to make sure my oxygens are correct. So 25 times 2 gives me 50. 26 and 1 will give me 26. Let me undo that 1. And then if you add these two, we're going to need a total of 76 oxygen. So we're going to divide that by 2 to put it in here because it is O2. So 76 divided by 2 is, let's see, 38. So that is my balanced equation. And with that, now is my ratio. One of these hydrocarbons, C25H52, is going to produce 30, or it's going to consume 38 oxygen gas molecules, 25 carbon dioxide molecules, and 26 water molecules, or moles. So 1 mole, 38 moles, 25, 26. Once we have that, we're going to go back to this one. We have it in grams, so we need to change it into moles. So 0.50 grams. I need to change it into moles. I do have the molar mass. Here I want the grams on bottom, so 350 grams per mole. And where's my calculator? So 0.5 divided by 350 will give me 0.001428. And I'm going to keep this in my calculator. I want to know how many oxygen, so I'm going to multiply by 38. Get 0.54. Oh, I messed up. 0.054. I started with 2 sig figs. I'm going to leave it at 2 sig figs. Okay, now I need 25, so times 25. So 0.036 moles. And then the last one, .037. Yep, so there we go. That's kind of how you solve it. Let me check my answers, make sure I did it correctly. It looks like I did. For 3b, we have the question, the empirical formula of something is C3H7. So remember, empirical formula is just a reduced form of whatever it is. So if we look back here, the empirical formula of C25H2 is, actually that's it. You can't really see 5 can't go into it, yeah. So that is but you can't reduce that anymore. But you could reduce some, so you could double it. So C6H14 is a possibility. We could triple it. So C9H, 9 times 27 is 50. 9 times, yeah, let's see. I could do this in my head. 9 times 7 is 69. No, 63. All right. Wait, am I doing that right? 3 times 7, sorry, 21. I can't do this. Anyway, so 3 times 9, yeah, okay. I was multiplying around. But anyway, I guess it could be nonan, but most likely it is hexane. I'm trying to think, nonan. I guess it could be nonan. Oh, okay. But hexane is the correct answer there. I guess 3 would work. Okay, so I'll accept both answers. All right, now letter D. 700 calories per mole of glucose. We want to know how many calories 14 grams is. So this is a ratio of 700 grams per mole, but I have grams. So I'm going to have to do some conversions here. So I have 14 grams. I need to change it to moles. So I want moles on top, grams on bottom, 180 grams. Then I need to know calories per mole. Oh, I just need calories. So I need to get rid of, so remember it's 700 big cal per mole. Moles on top, so I'm just going to put 700 calories on top per 1 mole on bottom. So the moles cancel out, the grams cancel out. So I'm just going to multiply across. 14 divided by 180 times 700 will give me 54.4 repeating big cals. I started off with, let me see how letter D was, 3D. 14 grams, so 2 sig figs. I'm just going to leave it at 54 big cals. Okay, so that would be the answer for that one. All right, for number 4, we have the following. We have C4H8 and C something H42 have the same empirical formula. Remember, this is just a reduction, so this is a 1 to 2 ratio. If I reduce this, it will be CH2, so 1 to 2 ratio. So if this is the same, it's just 42 divided by 2, so that will give me 21. So this will give us the same empirical formula of the 2, and I think that's it. All right, for number 6, you have paraffin again, and we want to complete this combustion. So combustion is going to require O2. I should use a different color. O2. it's going to produce CO2 and water. And we want balance equation 25, so 25 here. So now it's balanced. 52 divided by 2 will give me 26. And now I want to count my oxygen, so 50 here and 26. So 50 plus 26 is going to give me 76. Divided by 2 will give me 38. So there's my balance equation for that one. Now here's another combustion one. We have 57 grams of C7H16. So we want to know how many calories it's going to produce and also how many moles of CO2. So first we want to write the combustion equation. So C7H16 plus, remember it's going to use up oxygen and it's going to produce carbon dioxide, O2, and then there's another given 4700 kilojoules per mole. But I don't need to put it there because if once I balance this, it's going to give me what it is. Well, actually, I should keep that there, but just in case this is a 2 over here. So let's kind of balance the equation and make sure that this is correct. So I have C7, so that means I need 7 here. H16, so that means I need... Oh, I did it wrong. Shoot. Not O2, H2O. There we go. All right, let me fix it now. Go back to blue. All right, so C7, 7, H16, so that means I need 8 H2Os. Now I need to do my oxygen. 7, 2 is 14 plus 8. 14 plus 8 is 22, so I'm going to have 11 oxygens. I feel like I did something wrong. Let me check my answers. Oh, I did my answer key wrong. Look at that. Oh well. I will get this, at least I got this correct. So this is a balance equation. Let me just double check to make sure I did it right. C7, 7 carbons. H16, 8 times 2 is 16. 7, 2 is 14 plus 8 is 22 divided by 2. Yep, this is totally correct. So this is 42 per mole because I have 1 mole right here. Now I'm going to figure out how many of this. So if I have 57 grams, I need to find the molar mass. So 7 times 12.01, 16 times 1.01, and let me figure out my molar mass. So 7 times 12. Plus 16.16, that will give me 100.23 grams per mole. 57, let me make sure I got that right. 57 grams. So I'm going to have 100.23 grams on the bottom, mole on top, and that will give me my moles. And let's see what I want. I want both calories and moles of that. So I'm going to do this one first. So 57 divided by 100.23, and I get 0.569. Now I'm going to keep it in my calculator just to do it correctly. So moles of CO2, so this is right here. So the ratio is 1 to 7, so we multiply by 7, and I get 3.98. Here, let me see if I did it right, and then I want to know how many calories, so it's this many per mole, so I'm going to multiply by 4700 kilojoules per mole. The moles cancel out, I'm left with kilojoules, and I have 2672.8. Let me see, I started off with 2 sig figs, so I'm going to end with 2 sig figs, so it's about 2700 calories. Oh no, joules. I messed up. This is in kilojoules. Let me erase that. And what do we want? We want to know calories. So we need to convert it. So this is kilojoules. So I know the ratio. Let me see if I have enough room. I think I do. All right, first I need to convert it to joules because I know the ratio is 4.184, I believe, joules per calorie. So I have kilojoules here, so I want joules, so it'll be 1,000 joules per 1 kilojoule. Then I need to get rid of joules, so 4.184 joules per 1 calorie. So then I'm going to kind of simplify this. So 27 times 1,000 divided by 4.184, and I get about 6.39 times 10 to the 5 calories. And it's big cal. This is little cal, so I need to divide this by 1,000. And I get 638.8. So what do we start off with? 2 sig figs, so 640. Big cows. All right, so that will be pH 62. Let me know if you have any questions.